Section 8.6, comparing linear, exponential, and quadratic functions. To wrap up this chapter, we're just going to summarize the differences between linear functions, exponential functions, and quadratic functions. Linear functions is something we looked primarily at early in the year. Recently, we've been focusing on quadratics, and exponentials are something that we've looked at a little bit, but not too much in detail. Well, on the graph here, I have three functions drawn: a green function, a red function, and a blue function. Now, it's probably pretty easy to tell which one of these is a linear function because it has the shape of a line. The green one is a linear function. It has the equation y equals mx plus b, where m is the slope and b is the y-intercept. It could be written in other forms, standard form, point slope form, but it can be written in slope-intercept form. Y equals mx plus b indicates to us that it is a linear function, and this is what its graph looks like: a straight line. All lines are straight, but just to emphasize that. A quadratic is what we've been looking at most recently, so that should be pretty clear that this is going to be this blue function, which is a parabola. And a parabola that opens vertically has an equation that can be written y equals ax squared plus bx plus c. Now again, we've seen this in other forms. We've seen it in vertex form. We've seen it in intercept form. But the bottom line is that we could expand either of those and end up with this quadratic equation here. And so a quadratic has a shape like this. Anytime you see a parabola, it's going to be quadratic. And finally, the other one is called exponential. And that's something that's going to have the form of y equals a times b to the x. One thing just to point out is that x is only on the b, so we'll raise b to the xth power, whatever x happens to be, and then we'd plug in for a. But that's a separate thing for right now. And by process of elimination, that's going to be this red function here. You can see it seems like it's actually going pretty steady, and then all of a sudden turns up pretty quickly. And so that's the general shape of an exponential function. You can see just how fast it turns up, and when we say something grows exponentially, that's what we mean. It means it grows really fast. All of a sudden, it's just shooting up really straight, even though it was really level for a while. So those are just the three general types of graphs and equations that you'll see. If you can write something as y equals mx plus b, basically no exponents anywhere, you're talking about a line. If you're talking about something that has an x squared, maybe b is 0, maybe c is 0, but if you have an x squared, or could write it with an x squared, then you're going to have a quadratic that's the shape of a parabola. And if you have an x as an exponent, you're going to have this shape here, which is an exponential function. If you remember back to when we first looked at arithmetic sequences, we looked at patterns and tables to see if we could find a common difference. Well, we can actually do the same thing with these three types of equations here. These three types of functions to determine from a table, whether it's linear, exponential, or quadratic. So if I look at this first example here, I have to think about how I'm getting from each y term to the next. How do I go from 11 to 8, and then from 8 to 11, from 5 to 2, and so on. And so what I look for is what I call my first difference. And to find my first difference, I just basically do, 8 minus 11 is negative 3. 5 minus 8 is negative 3. 2 minus 5 is negative 3. Negative 1 minus 2 is negative 3. When my first difference is constant, as it is here, these are all negative 3s, that means that I have a constant rate of change. And one thing we looked at before is that is almost by definition a linear function. So if the first difference is the same, we're using a linear function. Let's try that same process with the next one. Negative 2 minus negative 1 is negative 1. Negative 1 minus negative 2 is positive 1. Now, you don't need to put a plus sign there. I'm doing it just for emphasis, although it certainly didn't look like it actually worked out all that well. There we go. Negative 1 to 2, that's 2 minus negative 1 is positive 3. And then 7 minus 2 is a positive 5. These are not constant, so this is not going to be linear. It's not a constant rate of change. And so what I can do is I can actually look at the second difference. And so what I do is I just take the differences of the first differences. So I have 1 minus negative 1 is 2. 3 minus 1 is 2. 5 minus 3 is 2. So my second differences are all the same. And whenever that's the case, I'm going to be working with a quadratic function. So first differences being the same makes it linear. Second differences being the same makes it quadratic. Let's take a look and see what would happen with this next example. I have a hunch that we know where we're going, but we should just make sure that we can see. If I start by using the common differences, I've got 2 minus 1 is 1. Then 4 minus 2 is 2. 8 minus 4 is 4. 16 minus 8 is 8. Okay, so those aren't the same. I guess I could try the second difference. 2 minus 1 is 1. 4 minus 2 is 2. 8 minus 4 is 4. Maybe at this point you see what's happening. As long as I continue doing this, I'm actually never going to get a common difference that's exactly the same. In fact, I had 1, 1, 2, 1, 2, 4, 1, 2, 4, 8, 1, 2, 4, 8, 16. By doing that, I actually didn't get any closer. I actually had the same sequence the entire time, so I was never going to get any closer. But the key is, there's another way to get there. Another way to get from 1 to 2, and from 2 to 4, and from 4 to 8, and 8 to 16. That is common. So let's erase what we just put down and try something else. One way to go from 1 to 2, instead of adding 1, would be to multiply by 2. And then the same thing is true from 2 to 4, the same thing is true from 4 to 8, and the same thing is true from 8 to 16. Each time I'm multiplying by 2. That's something called a common ratio. And with this common ratio, it's similar to a first difference or a second difference in that it relates one term to the next, but a common ratio actually represents the fact that this is going to be an exponential situation here. This is an exponential function. And it's something related to when we originally studied arithmetic sequences, it had to be addition or subtraction for a common difference. Common ratio creates something that we call a geometric sequence, which is something we may look at sometime in the future. But for now, what you just need to be aware of is if there's a common ratio, you're multiplying by the same thing over and over to get from one y value to the next, you have an exponential function. So just a brief summary here of this short little section. For a linear function, the graph is a line. The equation should have no exponents. And in a table, the first differences would be constant. In a quadratic function, the graph would be a parabola. The equation should have an x squared. And if it's factored, you'd have to multiply that out. Or if it's in vertex form, you could square the x minus h term to create your x squared, but it is in there even if it's hidden. And the second differences from a table would be constant. And finally, for an exponential function, the graph turns up quickly, steeply, as you can see there. The equation has an x as the exponent, and the consecutive y values have a common ratio when using a table. So I hope this summary is helpful in keeping track of what you learned today, and I hope that all of this makes sense.